Dear students, welcome to the chemistry class. Today's class, let us discuss about the aldehydes, ketones and carboxylic acids. In that, physical and chemical properties of aldehydes and ketones. So first let us consider the physical properties of aldehydes and ketones. So what are the physical properties we can observe in aldehydes and ketones? Mainly we have to observe the boiling points of aldehydes and ketones and also as well as the solubility of aldehydes and ketones. First let us consider the boiling points of the aldehydes and ketones. So what is the first point of the physical property of aldehydes and ketones is aldehydes and ketones are polar in nature. So as you know that, dear students, so carbonyl compounds, so aldehydes, ketones and carboxylic acids are the carbonyl compounds. The carbonyl compound is nothing but C double bond O. Here either two valencies are either it may be satisfied by hydrocarbon group or hydrogen atom, as we discussed in the earlier video. So now in this carbonyl compound, the carbonyl group is highly polar in nature. So aldehydes, ketones and carboxylic acids, all these compounds are having carbonyl functional group. Carbonyl group is acts as functional group. So whereas in case of aldehydes, either two groups are satisfied by alkyl group or any one hydrogen atom or either by two hydrogen atoms. Such kinds of compounds are called as aldehydes, we can say that. So now, so aldehyde is also having carbonyl group, ketone is also having carbonyl group, carboxylic acids are also having carbonyl group. So that's why commonly we can say that aldehydes and ketones are polar in nature. Why? Because in aldehydes and ketones there may be presence of carbonyl group. So this carbonyl group is highly positive by this carbon atom, this negative charge get by this oxygen atom. So that's why carbon is partially positive in nature, oxygen is partially negative in nature. That's why this carbonyl group is having highly polar in nature. So it can highly attracted by the nucleophiles and this oxygen atom is highly attracted by the electrophiles. So that reason we can say that this carbonyl group is always exists in the form of polar in nature. That's why the aldehydes and ketones are polar in nature. The second thing is the boiling points of aldehydes and ketones are always higher than that of hydrocarbons and ethers. So you are observing here aldehydes and ketones are having higher than that of hydrocarbons and ethers. So here hydrocarbons does not having any hydrogen bonding and ethers are also does not having any hydrogen bonding. Due to absence of hydrogen bonding in hydrocarbons and ethers, we can observe the higher the boiling point in case of aldehydes and ketones. So in case of aldehydes and ketones are having carbonyl functional group and it is having highly polar in nature. So that's case we can observe the higher the boiling point in case of aldehydes and ketones than that of hydrocarbons and ethers. So when we consider the comparative molecular masses of these aldehydes and ketones with that of hydrocarbons and ethers, so there we can observe that which of the following compound is having higher mass and which is having lower mass. So now let us consider here the comparative molecular masses of hydrocarbons and also as well as ethers and also as well as aldehydes and ketones. Dear students, now we are observing here the boiling points of aldehydes and ketones are higher than that of hydrocarbons and ethers. We have considered here hydrocarbons and ether. When we compare these hydrocarbons, ethers with that of aldehydes and ketones, the boiling points of aldehydes and ketones are having higher than that of corresponding comparable masses of hydrocarbons and also as well as ethers. So the first molecule is N-butane. N-butane is an hydrocarbon. This is an hydrocarbon of having the boiling point 273. Its comparable mass is 58. And methoxymethane, its comparative mass is 60 and its boiling point is 281. And propanol is an aldehyde. Propanol, the suffix al is there. This is propane. One all is nothing but aldehyde. Its boiling point is 322 and its comparative mass is 58. And acetone, it is an ketone. Ketone functional group is C double bond O either side. Two alkyl groups may be substituted to this carbon atom and its boiling point is 329 and its comparative mass is 58. And propane, one all, it is an alcohol. Alcohol is having 370, its boiling point and its comparative mass is 60. So you just observe here the masses of all these compounds are almost comparatively similar and it is very nearer to its boiling points. But whereas in case of the boiling points, you are observing here the boiling points are goes on changes. So this is an hydrocarbon. This hydrocarbon is having 273, and next methoxymethane, it is in ether. Ether is having higher than that of this hydrocarbon. This is 281, and propanol, it is an aldehyde. It consisting of 322 boiling point. Aldehydes is having higher than that of ethers and hydrocarbons. And acetone, it is having 329, and propanol alcohol is having still higher boiling point than that of aldehydes and ketones. So that's why I told you that here boiling points of aldehydes and ketones are lower than that of alcohols. See here, this is an alcohol. This alcohol is having 370. Here ketone and aldehydes is having 322 and 329 with that of comparative masses. So almost the masses are same. The boiling points are differ. So this is because of due to polar in nature of this carbonyl compounds. Aldehydes and ketones are having higher boiling points than that of ethers and corresponding hydrocarbons, whereas in case of alcohols there is a presence of hydrogen bonding. Due to presence of this hydrogen bonding in alcohols and presence of alcohols and carboxylic acids. So this is due to the presence of hydrogen bonding, absence of hydrogen bonding, correct, it is an absence of hydrogen bonding in aldehydes and ketones. Aldehydes and ketones, this is correct. So here the absence of hydrogen bonding in aldehydes and ketones. So that's why in alcohols there is a presence of hydrogen bonding, that's why its boiling point is higher. So next let us go for next point, that is lower aldehydes like methanol and ethanol is liquid. So here methanol is considered as an gaseous state, whereas in case of ethanol it is in liquid state. In case of higher hydrocarbons or higher aldehydes or solids in nature. So whereas if we consider the different kinds of aldehydes, methanol is considered as CHO. This is called as formaldehyde. Formaldehyde is nothing but methanol. The word root for this is 1. That's why it is methanol. Methanol is having always in gaseous state, and ethanol is having liquid in state, whereas higher hydrocarbons are nothing but propanaldehyde, butanaldehyde, vinylaldehyde, so etc. Those are all exist in case of solid states. And the next point is weak van der Waals forces between the molecules or dipole-dipole interaction is goes on increases with increase in molecular mass or comparative masses of the aldehydes and ketones. As the chain is goes on increases, the comparative mass is also goes on increases. As the mass is goes on increases, the weak van der Waals force of attraction is goes on increases, or dipole-dipole interaction is goes on increases due to association of the molecules in the compounds. The next point is the boiling points of aldehydes and ketones are lower than that of alcohols and carboxylic acids. So in case of alcohols and carboxylic acids, there we can observe the hydrogen bonding, whereas in case of aldehydes and ketones there is no presence of hydrogen bonding. So due to presence of hydrogen bonding in case of alcohols and carboxylic acids, it may takes the higher the boiling point than that of the corresponding aldehydes and also as well as ketones. So observe the point very clearly. In the first point what I have discussed, in the first point I discussed about the boiling points of aldehydes and ketones are having higher than that of corresponding hydrocarbons and ethers, but whereas in case of last point, boiling points of aldehydes and ketones are lower than that of corresponding alcohols and carboxylic acids. So this is because of absence of hydrogen bonding in aldehydes and ketones. So and also we have observed the different compounds and their boiling points and corresponding comparable masses of these aldehydes, ketones, ethers and alcohols. Now let us consider the next important physical property of these aldehydes and ketones is solvent, that is solubility of these aldehydes and ketones. Now let us consider the second physical property of aldehydes and ketones is solubility. So what happens the solubility of these aldehydes and ketones? The aldehydes and ketones, the lower aldehydes and ketones are soluble in water, because the lower aldehydes and ketones can able to form an hydrogen bonding with water molecule, so that lower aldehydes and ketones such as methanol and ethanol and propanol, these aldehydes can easily soluble in water. So whereas in case of as the chain is goes on increases, the aldehyde chain is goes on increases, means the number of carbon atoms is goes on increases, such as butanaldehyde or pentanaldehyde, so etc. Whenever the carbon atoms is goes on increases, there is a increase in the mass of the aldehydes and or ketones, and its comparable masses is goes on increases, the there is unable to form an hydrogen bonding with water molecule. There is a failure to form an hydrogen bonding with water molecule. That's why the higher aldehydes and ketones are unable to soluble in corresponding water molecule. Whereas in case of lower aldehydes and ketones, that is methanol and ethanol, so these can able to easily soluble in water. They can able to make a corresponding hydrogen bonding with water molecule. So when we consider the higher the compounds, so simply we can say that lower aldehydes and ketones are soluble in water, but while higher members of aldehydes and ketones are not soluble in water, because they failure to formation of hydrogen bond with increase in mass of aldehydes and ketones. So here, whereas the mass of aldehydes ketones goes on increases, means the chain of the aldehydes and ketones goes on increases. There is a failure to formation of hydrogen bonding. So whenever there is a failure to form an hydrogen bonding, it is highly impossible to soluble in water. Whereas in case of lower aldehydes and ketones are highly soluble in water due to formation of an hydrogen bonding. So if we consider a general formula for the aldehydes or ketones, so R C double bond O R, so it is ketone. Either you may consider the aldehyde, this is an aldehyde. So and water molecule is hydrogen, oxygen is highly electronegative, and here also oxygen RH. So here C double bond OH. So this is an aldehyde. So lower aldehydes can easily soluble in water due to formation of an hydrogen bonding with oxygen and hydrogen. Here also there is a formation of an hydrogen bonding with oxygen and hydrogen. So due to formation of an hydrogen bonding between water molecule and aldehyde, so this is an aldehyde, this is an water molecule, this is an aldehyde. The number of aldehyde molecules can able to make a hydrogen bonding with that of water molecule. So this is an water molecule. This water molecule can able to make a bond with aldehyde. Here also this water molecule can able to make a bond with aldehyde. So here there is a bond takes place between highly electronegative atom of oxygen with hydrogen, highly electronegative atom of oxygen with hydrogen. So due to this reason, so intermolecular hydrogen bonding is going to be takes place between aldehyde and water molecule. So that reason we can observe, so these are soluble in water. Solubility can take place, whereas in case of lower aldehydes and lower ketones, whereas in case of higher aldehydes and ketones, this bond is takes place in higher aldehydes and ketones. That's why the solubility is going to be decreases, whereas the number of carbon atoms in a chain goes on increases. So in such a case, how to dissolve such kinds of aldehydes and ketones? In such a case, the aldehydes and ketones can be dissolved in corresponding organic solvents. Solvents such as benzene, we can also consider. Benzene is an organic solvent, ether, acetone, etc. So those are all the organic solvents can be used for the solubility of an higher aldehydes and also as well as higher ketones. So next let us consider about the chemical properties of aldehydes and ketones. Dear students, let us consider about the chemical properties of aldehydes and ketones. So in chemical properties, we can observe the two types of important chemical reactions. One is addition reaction. So second one is condensation reactions. First let us discuss about the addition reaction. So what happens in addition reaction? So here aldehydes and ketones are having one functional group, that is carbonyl functional group. Here the aldehydes and ketones are highly polar in nature due to presence of carbonyl functional group. So let us consider the functional group of aldehydes. So this is, let us consider A, this is B, this is delta positive, this is delta negative in nature. So aldehydes, either maybe aldehyde or ketone is having highly polar in nature due to the partially positive charge of carbon and partially negative charge of this oxygen atom. So what happens here, this partially positive carbon atom can tendency to attract by nucleophiles, and this partially negative oxygen can tendency to attract by electrophile species. So here, how does it going to be takes place? The chemical reactions are going to be takes place because of partially positive charge of carbon and partially negative charge of oxygen. Because of this polarity, the chemical reactions will undergo with aldehydes and ketones. Now, so how does it undergo changes? So what happens? Ultimately, whenever the nucleophile is going to be attracted towards this carbon atom, this can also be considered as carbon. It can be, so when the addition of one substituent takes place to this carbon atom, means this lone pair of electron will excited to this oxygen atom. So ultimately what happens, this oxygen will get delta negative, so due to loss of electrons this gets delta positive. This is the formation of polarity due to attack of substituent to this carbon atom. Ultimately this pi bond is going to be cleavage, and the formation of a new bond takes place and cleavage of a pi bond takes place, and ultimately it gets negative charge, it gets positive charge. So this is about the formation of polarity. So this can also be represented as C double bond O, delta minus and delta plus. This is A, this is B. General form of aldehydes and ketones. So this is in general form of aldehydes and ketones can be represented like this. And now let us consider some chemical reactions of addition of HCN to this corresponding aldehydes and also as well as ketones. Let us consider the general mechanism of addition of HCN to aldehydes and ketones. Here, let us consider the addition reaction. The addition of HCN to any aldehydes or ketones. Here, aldehydes and ketones undergo nucleophilic substitution reaction. Nucleophilic substitution reaction. Let us consider the general mechanism. Let us consider the general mechanism for the addition of nucleophiles to any aldehydes or any ketones. Here, it consisting of two steps. So in the first step, what happens? In the first step, the attack of nucleophile takes place to the carbonyl carbon atom. And why? Because it is in partially positive in nature. The nucleophile is a negatively charged species. That nucleophile can easily attracted to the substituted to the carbonyl carbon atom, and oxygen will get partially negative in charge. So this undergo the first step. So what happens in the first step? In the first step, the attack of, this is generally A and B, any atoms or group of atoms let us consider, and next is nucleophile. This nucleophile, cyanide is a nucleophile. So here, how we can able to apply this nucleophile? So this can be added in terms of HCN. So HCN is in covalent in nature, but HCN directly we can't able to add. So we have to add this nucleophile in the form of base or alkali, that is in the form of sodium cyanide. So how to get this sodium cyanide? So when this HCN which when react with sodium hydroxide, that leads to the formation of sodium cyanide. This leads to the formation of sodium cyanide with elimination of water molecule. Sodium cyanide with the elimination of an water molecule. This sodium cyanide is an alkali. So this alkali which when added to this any aldehydes or ketones, the attack of cyanide takes place to this carbonyl carbon atom. So this will takes place in form of sodium cyanide. What happens next? The elimination of sodium, it will takes place. So what happens here? The attack of cyanide, carbon, here A, here B, general atoms or group of atoms. What happens? The attack of cyanide, this cyanide is a nucleophile. So next what happens? This oxygen gets a negative charge. So why? Because whenever the formation of a bond takes place, ultimately there is a cleavage of bond takes place. So this is universal method will takes place whenever the formation of a bond and cleavage of a bond takes place within a reaction ultimately. So this is an pi bond, easily cleavages, and this lone pair of electrons will shifted over an oxygen, and oxygen will get the highly electronegative and it will get still more electron density. So and it will let us consider as highly electron rich. So whenever this highly electron rich species of this addition product which when further reacts with proton, that is acid, so we have to add the HCN. So we have already added cyanide in the form of sodium cyanide. The remaining is hydrogen. That hydrogen will attack by that oxygen. Here step 2. In the step 2 what happens? When that carbonyl cyanide, so oxygen is highly electron rich in nature. Here the attack of electrophile. Firstly the attack of nucleophile takes place. Further in the second step the attack of electrophile takes place to this aldehyde. So ultimately the attack of this electrophile to this nucleophile. So there is a formation of hydroxyl group. So there is a formation of hydroxyl group. This is cyanide, this is OH. So this addition product is called as cyanohydrine. This addition product is called as cyanohydrine. This is an cyanohydrine is a product is going to be obtained. So when in the first step cyanide is acts as nucleophile, when this nucleophile is attacked by this highly electropositive carbon atom of carbonyl group of carbon atom, and this oxygen will get a negative charge. That negative charge is attacked by the highly electropositive, that is hydrogen electrophile. That electrophile will attack to this oxygen. Ultimately we are going to get an addition product. That addition product is called as cyanohydrine. So similarly we can add this HCN to any kinds of aldehydes and ketones. Not only for this general mechanism, this mechanism we can apply it for the number of aldehydes and ketones. Here A and B atoms or group of atoms can be replaced. This mechanism can apply it for both aldehydes and also as well as ketones. If you want to apply this mechanism for aldehyde, here you have to take an hydrogen, here also you have to take an hydrogen. That forms formaldehyde. When the formaldehyde which undergo reaction with HCN, hydrogen cyanide, that leads to the formation of a cyanohydrine. Cyanohydrine is a addition product. So this is about the mechanism of addition of HCN to any aldehydes and ketones. I have represented in the form of general mechanism. If they ask to write the mechanism for the addition of HCN to acetaldehyde, how would you consider the molecule of acetaldehyde? You have to add the HCN to acetaldehyde. So how will you consider the acetaldehyde? Acetaldehyde formula you must know. So acetaldehyde means here you have to change A is replaced by CH3, here B is replaced by H. This is CH3CHO is called acetaldehyde. When this acetaldehyde interact with nucleophile, that forms an CH3, here CH3, here hydrogen. So further what happens, this addition product, intermediate product reacts with hydrogen, that forms, so this is the acetaldehyde. Acetaldehyde cyanohydrine is going to be obtained. Acetaldehyde cyanohydrine is going to be obtained. So this is nothing but hydrogen. Here also CH3. Only the groups of atoms or group of atoms are going to be replaced. This is acetaldehyde. General mechanism we have represented initially. So after that acetaldehyde we have considered, when this acetaldehyde reacts with cyanide, that forms an intermediate. Further it interacts with electrophile, that forms cyanohydrine is a product. So next let us consider the one more addition reaction, that is sodium hydrogen sulfite or sodium bisulfite, we can also say that. So let us consider the second addition reaction. The second addition reaction, that is sodium bisulfite. So second addition reaction with sodium bisulfite. Sodium bisulfite, what is the formula? Sodium bisulfite. You observe the spell here. It is not sulfate, it is sulfite. It is SO3. So here also the addition of electrophile and nucleophile takes place. Here which is electrophile? This is an electrophile, this is an nucleophile. The attack of electrophile and nucleophile takes place. First what happens? First attack of electrophile takes place, nucleophile takes place. Further followed by attack of electrophile. Ultimately we are going to get an addition products. Such addition products can be named on the basis of the added reagents. So this is with sodium cyanide. Any aldehydes or ketones which when reacts with for example carbon double bond O. So this is an aldehyde generally. So or carbonyl compound, any carbonyl compound which when reacts with sodium hydrogen sulfite, so what it forms? So it leads to the formation of an addition product. First the addition of this nucleophile takes place, SO3H is going to be attacked. So carbon, here the attack of this nucleophile means SO3H is going to be attacked, SO3H is going to be attacked. So further oxygen will get highly electron density here, any alkyl groups. So further what happens? So further the attack of sodium to this oxygen. Why? Because this is electropositive, it gets electronegative when the attack of SO3H. After that sodium will attacks to this oxygen. Further what happens? Further proton transfer will take place. Further only the proton transfer will take place. Whenever the proton transfer takes place, that leads to the formation of C. Here O, H will comes up. Here this sodium will come, sodium. So this is aldehyde or any carbaldehyde. Aldehyde sodium bisulfite is the compound obtained. So aldehyde sodium bisulfite is the addition product. This addition product is the addition added by sodium bisulfite. This is an addition reaction takes place to this aldehyde. Generally if you consider here CH3, here H, this is acetaldehyde. This acetaldehyde which undergoes sodium bisulfite, that sodium bisulfite leads to the formation of sodium aldehyde sodium bisulfite compound. So this is acetaldehyde. So when you consider the CH3 and H, CH3H, here also CH3H, this is sodium acetaldehyde sodium bisulfite compound. Sodium bisulfite compound is the product you are going to obtain. Similarly, you may consider the plenty number of reactions. Here you may consider ketone, C double bond O. Here this is by R and R. General formula for the ketone is R, C double bond O, R, which when reacts with sodium bisulfite, this undergo produce CO, Na and SO3 Na. You can interchange the proton, here itself you will get the product. Directly I have written here. So these two steps are converted into single step. So proton transfer also I done in this reaction. So this is nothing but this is ketone sodium sulfite compound, ketone sulfite sodium sulfite compound. Further if you consider acetone, CH3 C double bond O CH3, the acetone formula is R is replaced by alkyl group or replaced by any alkyl compounds, hydrocarbon groups. So CH3 this forms an acetone or propanone, propane 2-one or 2-propanone is the compound. So this 2-propanone which when reacts with sodium bisulfite, that leads to the formation of and corresponding addition product. This is OH, this is SO3 Na. This is the product is called as, this is an acetone sodium sulfite compound, acetone sodium sulfite compound. This is an chemical reactions of aldehydes or ketones with HCN and also as well as sodium hydrogen sulfite. The addition of HCN mechanism is very important for the point of examination. The addition of HCN, first two steps we have seen in the previous discussion. So previous discussion alli ನಾವು first step addition of cyanide, next step alli addition of hydrogen. That mechanism is called as addition of HCN to any aldehydes and ketones. Next let us consider about the condensation reactions of aldehydes and ketones. So when the aldehydes and ketones are reacts with derivatives of ammonia, derivatives of ammonia are nothing but hydroxylamine is a derivative of ammonia, and also hydrazine is also derivative of ammonia, and third one is phenylhydrazine is also a derivative of ammonia, and 2,4 dinitrophenylhydrazine is also a derivative of ammonia. So what happens when these aldehydes and ketones reacts with derivatives of ammonia? there is ultimately the condensation reaction takes place between the derivative of ammonia and also as well as aldehydes or ketones. By the condensation of one water molecule, there is a obtaining condensed product. Those condensed product can be considered as some of the important chemical reactions of aldehydes and ketones. Now let us consider the second most important reactions of aldehydes and ketones is condensation reactions.